First of all, thank you very much, everybody, for joining us. One more seminar of CitAI. And today we have Rodrigo Agerri. So it's a pleasure, to introduce Rodrigo Agerri to you because, well, among other things, Rodrigo is a very good friend. Okay. And he actually did his, PhD with us at City University. So it's very nice to see him back, so to speak. But this is not the important thing, obviously, about Rodrigo's CV. What is important is that he actually is a very well-known researcher in the area of natural language processing. Is working in the IXA team, or Taldea, in natural language processing in the Basque Center for Language Technology. It's in the University of the Basque Country. And his area of expertise, is, among others, is precisely computational semantics and natural language processing is what he's going to talk about today. And as I said, he's a very well-known researcher in the area, in Spain and also obviously worldwide, leading many different projects, European projects mainly, and also the projects from the Spanish government and the Basque government as well. So without further ado, I think that is all I had to say, basically, about Rodrigo. And now the floor is yours, Rodrigo.
Okay, thank you. Can you hear me okay, or should I can make my... Okay, excellent. So thanks very much for inviting me. It's a pity I couldn't be actually in London. I was looking forward to be there during this spring. So it's a little bit of a disaster, but anyway, so we try to make the most of it. So, and again, thank you, and thank you everybody for coming. I'm working, like Eduardo said, in the Basque Center for Language Technology, which is ITS, and ITS in Basque means word, okay? It's a sort of acronym. So you can check everything about what we do in the links you can see in the first slide. The first one, in this center, we have two main groups, one that works with text, okay, and it's in natural language processing, usually what it is known, and I'm part of that particular subgroup of the center. And then there's another group in the H center that works with speech, okay, they do speech processing and synthesis and so on and so forth. And so forth. Just in case you are interested, you can check it out. So today I'm going to speak, I'm going to make a little introduction about a task in natural language processing that is called name entity recognition, okay? And in particular, we're going to look at the importance of representing words in order to learn to do this task better, okay? So it'll be a little bit of a historical tale, so to speak. So first of all, why name entity recognition? So for example, we have a European project that they finished a couple of years ago, 3 years ago. And in that project, that you can see the link at the bottom of the slide, was called Newsreader. The idea was to be able to automatically extract the relevant information in the domain of the automotive industry domain. Okay, the idea was to automatically, so we had 10 million documents in this particular project written in several languages, okay? And the idea was to be able to uncover relevant information about, for example, the takeover of Skoda Auto by the Volkswagen Group. So anyway, you can imagine a big collection of documents in several languages. And the idea was that the things you can see in red in this slide were the things that happened, okay? What we usually call events, okay? And so that was a huge project. This is a very difficult thing to do because in order to be able to recognize all the things that are in red, we need to do many subtasks in an area, natural language processing. So what we want to do here, in order to extract everything relevant from this collection of documents, is something like that, okay? We decompose the big newsreader overview into these subtasks. So first, we know that all these big documents are in a timeline. Okay, we have in this particular project we have 20 years of documents. Okay, about the automotive industry, and so we have the timeline. So one thing that will be nice will be to order not only the documents, but the events that actually are being talked about, to order them in a timeline, okay, order them chronologically. That's one thing. Another thing, obviously, will be to, a nice thing will be to be able to recognize automatically the participants in the events, okay? For example, some entities such as Volkswagen, Porsche, Skoda, and so on and so forth. Okay, it'll be also nice to link this information so we can say that in the takeover, the first event you can see in this slide, you can see that there was taking part Volkswagen was taking over Skoda, okay, and so on and so forth. But we have also some colors, okay? We also want to know, for example, whether this particular event, for example, the first one you can see on the left-hand side, the one that is in green, the takeover of Skoda by Volkswagen, is actually considered to be something positive, so to speak. Obviously positive from the perspective of the entity that is taking over other entity. Or we could have some event which is actually red, such as stepping aside, or in this particular case, the president of Porsche, okay, and from his perspective, it will be something for himself, obviously, negative. So it'll also be nice to be able to do this task. So the general, and then obviously we have events that actually are talked about in the documents, but obviously we have many events that are talked about in the documents but never happened, okay? For example, the takeover of Volkswagen by Porsche, okay? There are many mentions of this event, never happened. This is a very difficult thing to recognize automatically, okay? So summarizing, the things we like to do in our field, in information extraction, in this kind of semantic processing, if you like, it'll be something like that. So we have this huge number of documents. I like to say, okay, tell me everything that happened with Wendelin Wiedeking, I don't know how you say that, which was the president of Porsche, okay, until he actually steps aside, okay. So in order to do that, obviously we do this in one language, but I mentioned that in this corpus, okay, in this big collection of documents, we have many languages. Well, we have several languages, and so we want to do this across languages. We want to be able to realize, say, if you have a collection of documents on the left-hand side in English and in Spanish on the right-hand side, we like to recognize that events and participants are the same, and they are spoken about these events and these participants in different languages and in different documents. So we want to be able not only to do this in one language, but also to say, okay, we have the English part on the left-hand side, we have the Spanish part on the right-hand side, and we are able to sort of build something cross-lingual, which means that if you look at the second event, which is the unveiling of the long range 777, we should be able to say that in this particular document in Spanish, there was an event which is the revelar o revelado la versión de su avión 777, and we should be able to actually automatically say that these two events are actually the same, okay, in two different languages, in two different documents. So this is a very difficult thing to do. We managed to do something that was useful for professionals working in the documentation field, okay? So that the idea is that because there is a lot of documents to check, so our programs, so to speak, will help you to do all this checking, okay? And will give you what it is considered to be most relevant for humans then to check whether that is correct or not. So you can see some results here, and I will not explain a lot about these results. The idea is that the evaluation of these cross-lingual timelines of events and participants that we build automatically, when evaluated with respect to the timelines that are built manually by humans, you can see that the results are very bad. Okay, and that was the best results at the time in the paper. In a paper we published a couple of years ago, 3 years almost. Okay, so there's a long way to go. And one thing that obviously needed to be improved in this particular task of building these huge timelines, it was the recognition of events, the part of the being able to automatically assign positivity or negativity and so on and so forth, but also, which is the topic of today, is the task of name entity recognition, that is recognizing the participants of the events. So basically, going back to the definition of the task, basically what we call name entity resolution in natural language processing is just the following. You can see that we have some news about some disappearance of some person that is called Claudia Lawrence. And in this particular text, we've got a number of things that we like to be able to automatically extract. Okay, the ones you can see in blue are the ones that are considered usually name entities, or in most of the cases, proper names. Sometimes in the name entities are also included things that are not grammatically proper names, such as dates, ages, or maybe prices or monetary values and things like that. But just for the sake of the talk, just let's consider name entities what we usually understand as canonical proper names. Okay, the most common proper names we usually work with are those names of organizations, persons, and places. So you can see in blue here, and then the ones you can see in red are other mentions to these particular entities. Okay, we will not be talking about the red ones. Okay, this is done in another task that is called reference resolution, and what it means is that when by looking at the name entities, for example, Claudia Lawrence, okay, we should be able to automatically link Claudia Lawrence, or the pronoun her in this case, which is in the middle of the slide, with the antecedent Claudia Lawrence. Or we should be able to link the pronoun him to contact him with the name entity Peter Lawrence, okay, and so on and so forth. We can do this with proper names, but we can also do it with common names such as detectives, and this day, or usually will refer to detectives. So this is a whole task. We'll only be focusing on the ones that are marked in blue. So how do you represent these name entities in order to learn how to automatically detect and classify them in text? So basically, the task consists of two subtasks. On the one hand, we should be able to recognize that there is a span of text. Okay, in this case, the span is just the number of words of which the name entity consists of. Okay, in this case, Tim Cook is a multi-word entity, or Apple in this particular case is just a one-word entity or a unigram. And the second type is to be able to automatically assign the proper type or class. In this case, that Tipkun will be a person, and that Apple actually in this particular case will be an organization. So there are many variants of this notation I'm going to introduce now, but this is just the most standard one. So the way we represent this in text, we have a document, and we annotate the documents in the way you can see it in this slide. Okay, so we have Tim Cook, which is a multi-word name entity. So we mark that per token or per word, Tim is the beginning of the name entity, which is a person, and Cook is actually in the inside of the name entity, which is a person. And then those that are not name entities are simply marked as being outside the entity. Okay, this is the way we represent these encodings in order to learn the sequences of name entities or spans that we need to learn here. Okay, so there are many other variants, like I said, and there are also a big important variant I know I will not be working on here, which is the nested name entities. Okay, we will be working with, for example, entities such as the University of California. We will consider the wider scope, okay, the longest span, if you like. which in this case will be the organization, okay, the university. We will not be considering that the fact that inside this particular name entity we could classify another one that could refer to the geographical or physical entity, which could be California. Okay, we'll just be working with the first cases. And there is also a lot of literature on what is called fine-grained name entities, because I'll be working with coarse-grained name entities here, just 3, 4 classes, 4, 5, maybe 6. But there are many works that deal with dozens and hundreds of different types of name entities. Okay, this is another field. So I'm going to present some results. So I will explain very quickly what the results will mean, so you can more or less have an idea about the evaluation. So if we have, on the one hand, the way we learn, obviously, this task in natural language processing is that we have some gold, ideally, obviously, we have some gold data. Gold data means that the having humans annotating by hand, hopefully, a number of documents, okay? And then, so for example, for the main results I'm going to present for English, there'll be about manually annotated around 250,000 words, okay, in English. And so we have the gold data, like I said, that is divided in training, development, and test. So we use the training and the development for the developing of our system, and then the test for the final evaluation results, okay? That is customary. And then the system, obviously, is our system, the prediction that performs. And we compare the two, the gold standard with the prediction. And we calculate these two different metrics. Precision, on the one hand, is the number of correct, in this particular number of correct tokens that the system predicted, okay? So in this particular case, only one was correct. No, only one was correct, because just Apple was correctly predicted. B pair in team is not a correct prediction, because the correct prediction is the whole entity, is the whole span, okay? Team Cook is not, in this particular evaluation, is not good to have a partial match, okay? It's a strict metric. We need to have a whole match in order to be a true positive, sorry. So in this case, the precision will be 1/3, okay? 1 out of 3, okay? Out of the 3 entities that we needed to, the 3 cases we need to predict correct, we only predicted 1. And sorry, out of the 3 predicted, we only 1 was correct. And the recall is the number of entities we need to predict, which is 2, okay? Tim Cook and Apple. And we just predicted 1 correctly, which is Apple. This is all the results we are going to present here will be the harmonic mean between precision and recall. Okay, that will be all the results. So in order to learn name entity recognition and most of the tasks in natural language processing, we have 2 main components, okay, simplifying quite a lot. On the one hand, we have the, in the classification function we want to learn, I mean, we have 2 main components. One is the learning method. Okay, the learning method could be a linear classifier, or it could be nowadays a neural-based network, okay, neural network, or deep learning-based method. That's one part. Okay, another part is how to represent the data. Okay, the data we use to learn and to evaluate, which is in our case text, words. Maybe that's a lot to. It's a big thing to say. But that's the second big part, which is how actually are we representing properly the data we want to work with. And we know, and we will see, that all things being equal, the best representation of word representation will obtain or will help to obtain better results in this particular task. Okay, so we'll introduce very quickly simplifying a lot again, 3 main word representations. Okay, one which is traditionally called one-hot representation, Another one based on clustering methods, which is distributional semantic representations. And then we will introduce finally the vector-based word representations, okay? So the one-hot representation, the way we usually, when we have a big corpus, we represent this corpus or this collection of documents in a matrix, okay, which contains in the rows are the words, okay, and the columns is the vocabulary, okay. So what this creates is are very sparse matrices, okay, because if the vocabulary is very large, okay, we have a lot of columns, a lot of rows. What we represent here is just whether in this for one particular word, okay, we place them in a particular, we order them, for example, alphabetically, we place them in a particular position, and the vector that represents the particular word, it will be all zeros except the position in which this particular word occurs, okay? And that will be the representation. This is the most classic representation, and what happens here is that, for example, even for words that we will assume that are somehow related, okay, such as man, boy, woman, girl, and so on and so forth, there is in this particular representation, on the one hand, we have a lot of zeros, which is not very good, but also we cannot really discriminate, we cannot really say or infer any kind of relations between the words we are representing in these particular ways. Still, this representation has been used traditionally in machine learning to represent data, and also it has been used to represent natural language processing words, okay? And until 10 years ago, 15 years ago, maybe 10 years ago was the most used representation. This particular representation in natural language processing created what we call the out of vocabulary problem. Okay, that was summarizing a lot. That happens when you have in your training data, you have some words that appear in your training data, okay, some name entities, imagine, and some words that are part of these name entities, but then you don't have them in the development of the testing data. Okay, and this was what we call the out of vocabulary problems. That's because we couldn't relate words that maybe are similar and that frequently occur maybe together or in similar contexts. We couldn't do this with these representations. So there was an evolution how actually to obtain denser or richer or representations that somehow will allow us to relate words that we consider to be similar, okay? So from this particular idea, or this particular idea is based on a very basic and very old idea, okay? That is the one you can see here, okay? It's distributional similarity based representation. So the meaning of a word, quite simply, is given by the context in which it occurs, okay? This is the distributional similarity hypothesis. Or in the original formulation, you should know a word by the company it keeps, okay? This is a very common, very well-known idea, and what it allows us in this particular case, if we consider the word banking, okay, these two different senses of bankings will actually be represented by the number, by its context, okay? So we are going to be practical about what we consider context here, okay? And we are just going to be considered that the context of a word is the sentence in which it appears, okay? That for today it should be enough. So the words you can see around banking in this particular case will be so to speak, the representations of this particular word. So this idea will allow us to cluster similar words based on distributional information. Okay, and using a classic clustering algorithms, such as the one from Brown, we could actually create, using large corpora, large collection of data, we could actually take, say, the whole English Wikipedia, and we can try to cluster every word that occurs in there is in the English Wikipedia in a number of clusters. So you can say, okay, I just want all the words in all the vocabulary in the English Wikipedia. I wanted to have it in 1,000 clusters and see whether we can make sense of those clusters after all. Okay. So the kind of information, the kind of relations, so the kind of similarities we want to obtain from these clustering-based representations is that if even considering that this is an automatic process, okay, we take a big corpus like the whole Wikipedia, we cluster it automatically using some clustering algorithm, and we obtain all these different groups, even though in those particular groups could be things that maybe are very noisy or have nothing to do with many other words. If we are lucky, we'll have information that is useful for our aims. Okay, so for example, you can see on the, and this is real examples. Okay, the left-hand side box. Okay, those are words in Basque that refer to places. Okay, and all these words you can see that they have the same suffix, so the same particular case. Okay, Basque is a high inflected language. Okay, it's agglutinative, so you have all the morphological information as suffixes to the main word. Okay, so in this case we have Donostia, which is San Sebastian, and it's going to or to San Sebastian. Bayona, Bayonne, okay, in the French part of the Basque Country, going to Bayonne. Zurich, Kera, to Zurich, and so on and so forth. So we saw that by applying different clustering algorithms, for example, on the Basque Wikipedia, but any text is fine, we saw that all these variants of names of places with this particular case were clustered together. Okay, so and that was a very useful information to have, and I will show now why. So we took this idea, we experimented in the paper that is referred below with a number of languages. We use 5 languages: English, German, Spanish, Dutch, and Basque. We took a different collection of documents. For example, a lot of you can see here in the million words that were used for training these clustering representations. Okay, we took a big collection of Reuters documents, the English Wikipedia, the Google GigaWord 5th edition in English, and so on and so forth. Okay, we did that for every language. We calculated, I'm not going to go into details about these clustering algorithms, but we used 3 clustering algorithms. And we had all these groups of words with all these, a lot of, with this big collection of documents that for English, for example, have 5,000 million words. Okay. So why is this important? So we had the one-hot representation in which we didn't have any relations between words. But now, when we have on the one hand side, if you remember, we have the gold annotated data by humans, which is our training data. Okay, in this particular slide, we have this BO notation we also showed. Okay, and then we have some tests, that is some documents on which we want to actually predict our name entities with a learned name entity recognition system. Okay, so traditionally, using the first representation, the one-hot representation, which is just 1 and 0s, we'll have this training data, we have this test data, and we'll have some features. Maybe if we are using some linear classifier, some manually coded features, so that we'll be looking at things that are in the training corpus, such as number of engrams, or maybe if the word started in a capital letter, or and so on and so forth. Okay, but now we have more information because we have all this clustering based data. So we have, for example, one of these clusters, which is also in Basque, names. In the one you can see in the central part are names of places. Araba is just a county in the Basque Country. Gasteiz is a city in the Basque Country, España, Spain in Basque, and Ecuador in Basque, okay, the country, and so on and so forth. And we had all these clusters that, you know, all these words were clustered together in using the Basque Wikipedia, for example. So we know, for example, that even if in the training data, Ecuador code doesn't appear. So we have in the training data, we see Arabako Foru Aldundia. This is an organization. We have, again, the name of this county, which is a place. We have the name of this city, which is also a place in the training data. So we give this data to an algorithm. We try to learn these entities. And so, but then we realize that when we are going to test, we don't have any sample of Ecuador. Okay, we don't know whether Ecuador, in this particular case, is a country or what. So in this particular, using these new representations, we know that because we have all this Basque Wikipedia clustered together, we realize that things we see in the training data are related with things we haven't seen before and that occur in the same cluster. So this is a strong hint that if Ecuador, in this particular case, goes together, frequently occurs together, or in contexts that are similar, it will actually be clustered with names of other places in Basque. So we can just relate this information and say, okay, I haven't seen before Ecuador, but there's a there's a lot of evidence in my data that it goes together with these other places. So this is a very simple technique, and it worked surprisingly well. Okay, in a paper we published in 2016 in artificial intelligence, just using this technique for 5 languages. This is the results for English. We still the best that we obtained for English. In this, there is a data set that is called Connell 2003, which is just an English annotated data on which you can train and evaluate your systems. We obtained the best results up to that date, okay, using this very simple technique. Okay, just instead of what we did here at the end of the day is to obtain better representations, okay, representations that allow us to actually say, okay, there are things that always or a lot of times happen together, so let's try to relate them. Okay, this is the idea. So at the time, if we look at the evaluation of results for this particular task in this, since 2003, where we started evaluating our systems in this particular data set, we can see that, well, our system, which is marked in a red point here on the timeline, it was at the time the best result. But since then, obviously, in the last 3-4 years, so you can see that it took like 10 years almost to actually go from 90 F1, 90, which is the harmonic mean of precision recall, to the next step, okay, almost 10 years. And what happened only 3 years ago in 2017, 2018, is that there was a big change in our area, like in almost any other area in artificial intelligence. Perhaps natural language processing was a little bit slower in adapting the deep learning techniques and the way of representing words for deep learning, but this was the big change. Okay, we can see that after 10 years of improving very slowly the results on this particular data set, then suddenly there is a big improvement. So let's see why there is this huge improvement. What happened? Okay. So, well, just to say that our system using these clusters worked very well for many languages, very different between them. So you can see Basque, you can see English, Spanish, Dutch, and also German. And we obtained the best results for every language and for every data we used in order to evaluate our system using this idea of clustering words, okay, for name entity recognition. So what happened, like I said, 2-3 years ago? So what happened is that we instead of representing words in a discrete way, okay, just at the end what we are doing is just, okay, this word, all these places should go together. Okay, so there was a new way that comes of representing words that comes from the neural network, using neural network techniques and from the deep learning community. And the idea was simply to represent a word meaning as a dense vector, or a vector in a particular vector space. Okay, so for example, the number of the meaning of linguistics, this word linguistics in a corpus, will be given by the a vector you calculate in relation to the other words that occur in the corpus in a particular vector space that is predefined. Okay, we will see very quickly what this means. So it means that if we have a matrix again with our vocabulary, and then one hot representation, we had as many dimensions in our matrix as words there is in the vocabulary. So it was very sparse matrix. So in this particular case, we can say, no, I want my word representations to have only 100 dimensions. I don't care if the English Wikipedia there is, I don't know how many million words. I just want every word to be represented by a vector, by a matrix that consists in the rows will be the number of words there are, and the dimensions will be a predefined value or the number of dimensions there is in your vector space. So you have the representation of dog will be given in this particular case by just a real value vector, and cat and lion and so on and so forth. So obviously, when you have words represented in vector spaces, you can obviously, for example, do something very simple, which is calculate the proximity between these words using something like cosine similarity, which is a very simple thing to do. Okay, because you have all these words placed in this particular vector space. There are many now. There was a big paper working on that in 2013 by Mikolov, and the technique was called word2vec, and that was the original idea. There are since then many other ways of doing more or less the same idea, but with different different particularities and so on and so forth. But the basic idea is that you reduce again the dimensionality in which you represent the words that they are in your documents. Okay, and then the second important issue here is that you can actually calculate and actually try to infer how close or how far the words are in this particular vector space. Okay, so one will think that dog and cat will be closer than dog and Paris. Okay. So the idea, well, anyway, so if you have a very nice contextual, a nice vector-based representation, so you have things, these points will be words, okay, and there'll be words that are in proximity in this vector space, okay, such as refrigerator and oven and so on, or maybe you have names of cities and so on and so forth. So what happened with this representation, while interesting, is that you can see that we have only one representation for each word. Okay, so one word, regardless of how many meanings this particular word can acquire in context. Okay, for example, bank in English, which is a very common example. Okay, bank is polysemous. But in this, using this particular technique, the word bank will only have one vector representation. So you don't represent polysemy in this particular vector-based representations. But since then, and this is where the big steep part of the results in imagery recognition came, so, there was another big development. Is that the idea was simply, in order to calculate only one vector representation for one word, okay, for regardless of how many meanings or how many senses this particular word may have in context, is okay, let's try to actually calculate these representations in context. Let's just be very practical again about the context. Let's consider that one sentence is the context, and let's say, okay, if Washington could be a last name or could be a state or a city or a sports team and so on and so forth, let's try to actually have for every of these different senses that the word Washington could actually acquire according to the context, let's give to every different occurrence a different representation. Okay, And this is what is called contextual-based representations, or contextual-based vector representations for words. Okay. This is one idea. Another idea is that so far we have been working with words. Okay. And words are sparse by definition, especially if you work in high inflected languages such as Basque, because the vocabulary is much larger. So, and if you have more vocabulary, it's more difficult to actually do all these tasks. Okay. So if you want to reduce the vocabulary, what you you benefit from actually having less things to work with. Okay. So you have less out of vocabulary words. So another big idea, apart from the learning this in context, was, okay, let's, instead of learn these representations for words, we are going to redefine the meaning of word, of what a word is. Okay, what we are going to do, I'm just going to skip this. What we are going to do is, if we want to calculate the representation of Washington, okay, what we are going to consider Washington is not just the word Washington as usual in linguistics. What we are going to do is, we are going to take Washington in a sentence. Okay, let's just consider the sentence: George Washington was born in whenever. Okay, that's our context. So the representation of Washington is going to consist of the output given by two different recursive neural network, one going forward and another one going backward. And what we feed to these neural networks is character or letter, in this particular case, based representations, okay, from the beginning of the sentence until the last character of the word we want to represent. That's the red arrow. So and then we do the reverse operation. We go to the end of the sentence, we take the last character, and we go all the way to the W, okay, in this case. So what we do here is we say, okay, the word now is the concatenation of all the representations for all these characters that go from the beginning of the sentence to the end of the word, and the opposite for the backward representation. And we concatenate these two representations, and this is the meaning of Washington. Okay, which is a very weird thing to say, but incredibly effective. Okay. The third idea, we have the context, we have the character-based representations. We don't work with words anymore. Words are considered to be sequences of characters. The third idea is the idea of transfer learning. So what the idea is very simple. We learned, okay, we take, like for the clusters, we take big corpus, okay, the larger the better. We learn these representations. We learn this in a language model, okay, and I'm going to explain how this language model is learned. But we learn this in an unsupervised. That is just we feed raw text to a neural network in order to learn a particular task. The task is just to, given a sentence, you just mask one word and you say, okay, what's the most common word here? What's the next word that is going to appear after this sequence of words? So this is the way this language model is learned. But the idea of transfer learning is very simple. Is we learn a big language model which consists of all these character-based contextual representations for English, say, okay, and we can apply this particular language model, okay, to a number of natural language processing tasks, such as name entity recognition. But we can apply, and what this means is that suddenly we have a lot of knowledge in a model, in a language model, character-based, with no sparse representations, okay, and with context-based calculated representations for Washington. Every occurrence of Washington in different sentences will have its context, okay, and we can apply all the same model to many different tasks. And these three ideas means that suddenly in these particular evaluations we suddenly were improving with the FLAIR embeddings, which is what I just explained. We just improved 2 points in the results in this particular task, in this particular data set, which is a huge improvement. Okay, it's very difficult to improve 2 points in this particular data set. And so I'm just going to be finishing. Okay, there is a new twist to these representations, which is, okay, so far we have seen, okay, we have representations for English, we have representation for Basque and for Spanish, and we calculate them separately. So now we have in a new way of new architecture, which is called the transformer, that I'm not going to explain, but there are now new neural network-based architectures that learn all these word representations for many languages. So what they do is actually they map representations for 100 languages in the same vector space. Okay, so for example, you can have and this is the multilingual BERT is calculated with the Wikipedias, the biggest Wikipedias for 100 languages. So that means that you can take this model and apply it to English or to Basque or to Spanish or to whatever you like and obtain very good results. So there is a hitch here, which is, and with this I'm finishing. So this we have these very nice word representations, context-based, very dense, very rich. We can do we can say that this word is next to the other, but there are differences between languages. You can do this with English and Basque, but we realize, for example, that for Basque, which is a less resource language, but for any other smaller languages such as Italian or so comparative with even big languages from big countries, but compare in resources with English, okay, they have many less resources. We realize that, for example, working with Basque, that in Basque you can see here in the Basque morphology that in Spanish house, which is casa, okay, etxe. So we have all these different words that can be inflected, okay, all these different ways of inflecting the same word in Basque. This doesn't happen in English, doesn't happen in Spanish. This is one issue. Another issue is that when you calculate these big multilingual models, okay, you are actually using the same number of strings, which is all these character-based representations, for English, for example, with the English Wikipedia that contains many more million words than the Basque Wikipedia. There's another issue. And another issue is that the way you represent the parts of the words in these representations are not linguistically intuitive for Basque. We realize that in the multilingual model distributed by Google, the multivert, which is distributed by Google, the way that Basque words are actually splitted is not correct, okay, or is not intuitive, so to speak. So we just did, what we did is, okay, let's correct this way of representing words in Basque. We do them linguistically more intuitive. We'll take one corpus containing not a big corpus. We'll train the same architecture used for the multilingual model, but only for Basque. And let's see what happens in name entities. So the results you can see here, and with this I finish. You can see here the results using cluster-based, which is the one on the baseline, 76 in F1. You can see the multilingual BERT official model from Google for 100 languages in Basque, 81, much better than the previous best results for this particular task in Basque. And you can see the new result by our take by correcting the way these representations are built, these language models are built for Basque, okay, using this BERT architecture, which is a huge improvement in only 3 years. Okay, it's more than 10 points in F1, which is just amazing. This is amazing. So with this, I will finish. We also apply these new representations and all these ideas to Spanish, a big corpus in Spanish compiled by the Academy of Spanish Language. We won using these ideas of combining different, doing better representation for Spanish as we did for Basque, and that's it. At the end, the take-home message is the machine learning or deep learning mechanism is important, but for many tasks in natural language processing, it is very important to actually have a very good representation, a representation of words that will allow you to actually to actually make comparisons or calculate automatically distances or similarities between words and so on and so forth. So thank you very much. And if you have any questions, I'll be happy to answer.